pick any real number, any one. I can tell you one thing about it, that is almost certainly true, and it is a number nobody chose. Here is that number, 2.68545200010, and on and on. It is called Khinchin's constant. And to see it, you do two things to your number. You take its continued fraction, and you take a geometric mean. Do that for almost any real number on the number line and you will land exactly on Khinchin's constant. It is hiding inside almost every real number, and nobody on Earth has been able to prove it is hiding inside any specific one. So what is a continued fraction? You take a real number, you split off the integer part, you flip what is left, you split off the integer part again, you flip what is left again, you keep going. What you get is a list of integers, a 0, a 1, a 2, a 3, and so on. The first is the whole number part, the rest are the denominators you keep flipping. Every real number has one, and they are weirdly beautiful. The golden ratio, its continued fraction is 1, 1, 1, 1 forever, nothing but ones. Square root of 2. Its continued fraction is 1, 2, 2, 2, 2 forever. After the first one, it is all twos. Now Euler's number E, a pattern but a stranger one. 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8. Every third coefficient ticks up by 2. And then there is pi. 3, 7, 15, 1, 292, 1, 1, 1, 2, 1, 3, 1, 14. No pattern, not that anyone has ever found. 4 famous numbers, 4 completely different expansions, or so it looks. Now here is where it gets strange. Take the list of coefficients after the integer part, a 1, a 2, a 3, all the way out to a n. Multiply them all together. Then take the nth root, that is the geometric mean of the coefficients. Call it Gn. Run this on the golden ratio. Every coefficient is 1, so the geometric mean is 1, always. Gn equals 1. Run it on square root of 2. Every coefficient is a 2, so the geometric mean is almost exactly 2. Gn goes to 2. Run it on E. Every third coefficient blows up forever, so the geometric mean blows up too. Gn goes to infinity. Every famous number you pick gives you a different answer, so there cannot be a universal one, right? Aleksandr Khinchin, 1934. He proved a theorem that I still find hard to believe. Take a random real number, any random real, pluck one off the number line by pure accident. With probability 1, the geometric mean of its continued fraction coefficients, as n goes to infinity converges, and not just converges to one specific number, 2.68545200010. Khinchin's constant k0, same number. Almost every real. The golden ratio misses it. Root 2 misses it. E misses it. All the numbers we care about, at least the ones we know by name, miss it. They are the measure 0 exceptions. Everybody else, every generic real number, hits k0 exactly. So let us watch it happen. Here is pi. I have computed 10,000 of its continued fraction coefficients, and here is the running geometric mean, plotted against the log of the step count. For the first few dozen terms, it is chaos. The 292 in pi's expansion smashes the running mean upward, then it crashes, then it ticks up, then it oscillates. But keep watching. By step 1000 it is getting close. By step 10,000 it is sitting almost exactly on 2.685. Pi is apparently not special. Let us try another number. Euler-Mascheroni gamma, the constant from the harmonic series. Nobody even knows if gamma is rational. Take its continued fraction and run the same experiment. Wild at first, then the geometric mean settles, and lands on k0. Natural log of 2. Same story, chaos, then calm, then k0. And here is the one that still breaks my brain, k0 itself. Take Khinchin's constant, take its continued fraction, take the geometric mean of those coefficients, and what do you get? k0 again. 4 chaotic sequences, 1 attractor, and I should tell you something uncomfortable. Nobody has actually proven that any of these 4 does what I just showed you. For every single one of them, we have checked millions of digits and they all head to Khinchin's constant. But nobody has a proof for any of them. The proof that an average real number hits k0 uses a beautiful change of perspective. It starts with something called the Gauss Map. The Gauss Map is this. Take a number between 0 and 1, flip it, throw away the integer part. What is left is another number between 0 and 1. Call it t of x. Now do it again, and again, and again. What you get is an orbit, a sequence of numbers jumping around in the interval 0 to 1. And here is the identity that makes it all work. If you track one of those numbers and you ask what its integer part was before you threw it away, you get the next continued fraction coefficient. The continued fraction is not a list of digits, it is an orbit. The Gauss map is a dynamical system. And like every dynamical system, it has an invariant measure, a way of weighting regions of the interval such that the weight does not change when you apply the map. For the Gauss map, that measure has a name. It is the Gauss measure, 1 over the natural log of 2 times dx over 1 plus x. And now comes the theorem that lets Khinchin win. Birkhoff's ergodic theorem. It says that for an ergodic system like this one, the time average of any function along an orbit is equal to its space average under the invariant measure. Plug in the function log of the integer part of 1 over x. The time average is the average log coefficient. The space average is an integral against the Gauss measure. They are equal, exponentiate, and the limit of the geometric mean becomes a single explicit number. So what is that explicit number? The integral we ended with splits apart because the integer part of 1 over x is piecewise constant. It equals k on the interval from 1 over k plus 1 to 1 over k. Fill in the pieces, and the integral becomes a sum. Sum over k from 1 to infinity of log k times the integral of dx over 1 plus x from 1 over k plus 1 to 1 over k. Do that inner integral, clean up the logs, and the answer becomes a logarithm base 2. What you end up with, written as a product, is this. k0 equals the infinite product over k of 1 plus 1 over k times k plus 2 raised to the power log base 2 of k. That is a closed form, and it converges. There is only one problem. It converges slowly, very slowly. The kth term differs from 1 by something like 1 over k squared, which is no good at all if you want, say, a million digits. In 2016, Antonio Simó used specialized numerical integration against the Gauss measure and beat the sum on its own terms. He computed k0 to 1 million decimal places. That is still, today, the record. No efficient digit extraction formula exists. Nothing like a BBP algorithm for pi. We have the formula, and we cannot go fast. So let me close with 3 questions that I find uncomfortable. First, is Khinchin's constant rational? Unknown. No closed form in simpler constants is known either. Nobody has connected k0 to pi, or to e, or to anything else we already understand. Second, does pi actually satisfy Khinchin's theorem? That is the geometric mean of pi's continued fraction coefficients equal to k0? Empirically, yes. Provably, no. We have no proof for pi, or for gamma, or for ln2, or even for Khinchin's constant itself. Third, the weirdest one. Khinchin's theorem is a measure-theoretic statement. It says almost every real number on the line behaves this way. But in 90 years, not a single named real number has ever been proven to be one of them. It is the constant inside almost every real number, named explicitly, inside none.